welcome back to the Ephemeris podcast. I'm your host, Aphelion, and this is the last episode of 2023. Thank you so much for tuning into the podcast this year and supporting this journey. Even if this is your first time seeing this podcast and this channel, it has been a really, really fun year, and I'm looking forward to season 3. And I should mention that this episode also marks the end of season 2, which is pretty wild because if you can imagine where we started at with like Vedas and cosmic eggs, and now we're ending with some of the most cutting edge astrophysics and cosmology today. So, yeah, it's quite a big jump from things like a cylindrical Earth to field unifying space and time and black holes and gravitational singularities. So we've come quite a long way from sort of the beginning of civilization, I guess I should say. But anyways, today's episode, as a wrap-up to the whole season, will be on Stephen Hawking, and he was a theoretical physicist and cosmologist, and the one thing he is most well known for is Hawking radiation. So we will look into that and much more in this episode. But first, we must start with our biography section, which is very much tradition. So, Stephen Hawking was born on January 8th, 1942 in Oxford into a family of physicians and a dad who wanted him to study medicine. In 1959, Stephen Hawking began his post-secondary education in the University College at Oxford, and he received a first-class bachelor's degree Bachelor of Arts in Physics. And I didn't actually know that there were things like first class and second class degrees, but apparently that's a thing in the UK. Hawking then moved on to Trinity College at Cambridge in 1962, and he obtained a Doctor of Philosophy in Applied Mathematics and Theoretical Physics in 1966 with a focus on cosmology. A well-known part of Stephen Hawking's image is his speech-generating device, which was necessitated by his worsening motor neuron disease, and he was diagnosed with the disease at the age of 21 in 1963. The motor neuron disease isn't the exact reason he was in need for a speech-generating device. I forget what exactly the thing was, but just in general, his health due to the motor neuron disease was worsening, unfortunately. So Hawking was a fellow of the Royal Society, a lifetime member of the Pontifical Academy of Sciences, and a recipient of the Presidential Medal of Freedom, which is the highest civilian award in the United States. And Hawking passed away at the age of 76 in 2018. And in all honesty, respect to the man for making it that long. His doctor said he was only going to last 2 years after he was diagnosed. So, yeah, let's look at the cosmological progress that was made by Stephen Hawking's work now. So, let's backtrack to Hawking's doctorate years for the beginning of some of his influential work. During the time that he was doing his doctorate, the steady-state model of the universe was quite popular, and the main thing to note about this theory, in terms of its definition, is the density of matter. The density of matter in the model remains constant because matter is being created at a steady rate, and the steady-state model adheres to the idea that the observable universe is the same at any time and place. And to put this in other words, if you zoom the scope of the universe out as much as possible, all forces kind of offset in the universe, and they create no inequalities, or very, negligible ones. So those are sort of the themes of the steady state model. But there has been evidence coming out as well during this time that is turning the tide against this model and toward the Big Bang Theory. One such piece of evidence is the cosmic microwave background and its detection, which I believe happened sometime in the 1950s. And, now we have the luxury of looking at pictures of the cosmic microwave background, so we can kind of understand that there is quite a lot of inequality that would go against the steady state model. Um, but at the time, obviously, maybe we don't have such visual details about um, the cosmic microwave background. So we have these two theories that are sitting in front of Stephen Hawking. But there is one thing that is going to tip the scales in terms of which universe model Stephen Hawking prefers. It's a theorem developed by Roger Penrose. The essence of the theorem is that given reasonable conditions between matter, energy, and volume, which I don't remember if he uses the weak energy condition or the dominant energy condition, but that's besides the point. Given reasonable conditions between matter, energy, and volume, of course, a black hole must have a geodesic incompleteness, or better said, a gravitational singularity of some sort, either a space-like or a time-like. So let's talk about a geodesic incompleteness. I'm not going to get completely into sort of how the vectors of a geodesic incompleteness work, because it's very, very complex. All you need to know is that a geodesic incompleteness occurs in one of two ways. In a gravitational singularity, where mass is forced to compress to a single point, or in a gravitational singularity where light is infinitely curved, or, light comes from a region that is infinitely curved. So what in the world does this have to do with Hawking? This whole theorem developed by Penrose. Hawking used the ideas created by Penrose here to add some important details about the Big Bang itself. He stated that the Big Bang event could be traced back to using the idea of a geodesic incompleteness, which makes sense. You could say, we consider the Big Bang event to be this implosion where a huge amount of matter and energy and light is being released and generated. And the characteristics of this Big Bang are likely to contain geodesic incompletenesses that we can kind of track back a little bit. But that's kind of my understanding of what Hawking did with the Penrose theorem. I'm sure it's much more complicated than that, but I've kind of put it in a way that I see fit to understanding how he did that. So Hawking wrote his PhD thesis on these ideas, and he expanded on the Big Bang theory, and he stated that the universe started from a singularity. And so he continued his work on these ideas with Penrose himself in the early 1970s. Not necessarily a side effect, but another additional thing that came out of Hawking's work on universe models is sort of making black holes and gravitational singularities a little bit more real, because Einstein himself, who designed the theory of general relativity and field equations, was not confident in the existence of an actual black hole in the real universe. And so, so that's sort of one thing that came out of this. Because at this point, we do not have here is literal evidence of a black hole. That only comes around, I think, maybe a couple decades later. But basically all we can do at this point is what Stephen Hawking did, and work a little bit more towards singularity theorems and proving that they actually exist. So investigating black holes is where Hawking's work will go after these revelations, I guess you can call them. Hawking postulated the second law of black hole dynamics. The first is that for perturbations of stationary black holes, the change of energy is equal to a combination of the change in area, angular momentum, and electric charge. Angular momentum and electric charge are two characteristics we've mentioned before, and it's no surprise that they change if there's some sort of change in energy. There's a lot of math that goes behind this first law as well, which I'm obviously not fit to bring up, but yeah. A statement that was given about the first law, which I think is interesting and might bring a little bit more insight to the law itself, it goes like so. Quote, "In fact, the effective temperature of a black hole is absolute zero. One way of seeing this is to note that a black hole cannot be in equilibrium with a black body radiation at any non-zero temperature, because no radiation could be emitted from the hole, whereas some radiation would always cross the horizon into the black hole. So yeah, this is talking about this whole effective temperature, how it has some double standards that won't allow it to be absolute zero, and how that might relate a little bit to the change in energy and sort of black hole dynamics as it's intended to do. So there's a zeroth law that comes before the first, which makes it a total of 4 laws, right? That states that the surface gravity of a stationary black hole is constant at the horizon. It would be a little bit unjustified for me to just leave this explanation as B, because I do want to bring a little bit of clarity to some of these ideas. So let's look at the law this way. If we have a black hole with no changes in energy, right, suppose, and an environment surrounding it with no macroscopic changes in energy, we can say that both objects are in thermodynamic equilibrium with each other, because that's quite literally the definition. Now let's imagine the horizon to be between these two objects and in thermodynamic equilibrium with both the black hole and the surrounding environment. Then the horizon is in thermodynamic equilibrium with the black hole, which sounds pretty obvious. So these are kind of we know this about the thermodynamics of a stationary black hole. And through lots and lots of math, we use these thermodynamics in this situation due to quantum mechanics and relate it to space-time geometry. And I can't really break down the mathematics for you because it's very complex, and that's just something I cannot do. But all in all, at the end, we land on the fact that stationary black holes will have the property of a killing horizon, which I think by textbook definition is a null hypersurface, which again gets into a little bit of geodesics, but that is the fact of the matter. Stationary black holes will have the properties of killing horizons, which implies that the surface gravity is constant. So yeah, that's pretty much the furthest I can go with breaking that down. So after the 0th and first laws of thermodynamics, which are expanded by Hawking in collaboration with James M. Bardeen and Brandon Carter in a paper, they get into the second law of black hole dynamics, which states that the event horizon cannot shrink. It states that the event horizon is a non-decreasing function of time, or its area, and so the horizon area can only stay the same or grow. The third law, which comes after that, states the necessity of surface gravity to form a black hole. The explanation given for the law, because this one doesn't have as much mathematics, it goes like this. Quote, for example, if one tries to reduce the value of K, surface gravity, of a curved black hole by throwing in particles to increase the angular momentum, one finds that the decrease in surface gravity per particle thrown in gets smaller and smaller as the mass and angular momentum tend to the critical ratio for which K is 0. So a curved black hole, just to be clear, is one that only has angular momentum. So basically this quote is explaining changes in rotation to an already rotating black hole. And so what the quote is saying is essentially the derivative of surface gravity shrinks with this value, and so K will never actually reach 0. And after this, after these laws of black hole dynamics, Hawking deviates towards quantum mechanics and gravity. In 1974, Stephen Hawking shows that black holes emit radiation known as Hawking radiation. Hawking radiation is predicted to be too minuscule to be detected by today's best telescopes, which I think would be interesting to prove that it actually exists, because it is still theoretical in the sense, and it's an element of predicted black hole evaporation. But that would mean that black holes have to shrink, right? How does that make any sense? I thought we just talked about, the second law of black hole dynamics, where the event horizon won't shrink. Well, during his time working on quantum stuffs, Hawking realized this, or Hawking realized that black holes might actually have entropy, and so he actually changed his mind on some of these ideas he was inspired by two, um, I believe it was European scientists in 1973. So, yeah, he had a change of mind, and an online article puts the essence of the discovery of Hawking radiation quite nicely. So here it is. Quote, Stephen Hawking used quantum field theory in curved spacetime to show that in theory, instead of canceling each other out normally, the antimatter and matter fields were disrupted by the black hole, causing antimatter and matter particles to quote unquote blip into existence as a result of the imbalanced matter fields and drawing energy from the disruptor itself, the black holes, effectively draining energy from the black hole. In addition, not all particles were close to the event horizon, and the ones that were could not escape. In effect, this energy acted as if the black hole itself was slowly evaporating, although it came from outside of it. So, yeah, basically what's being described here is the fact that we have antimatter and matter fields that are in slight imbalance, which will cause just, matter to blip into existence, and so this will create Hawking radiation. So, additionally, Stephen Hawking, in postulating black hole radiation, notes its difference from good old thermal radiation because thermal radiation is more statistical, and black hole radiation is more suited to the data. So, yeah. That's what we got for Hawking radiation and some of Hawking's work on black holes and cosmology. One thing I wanted to note that was interesting is that Stephen Hawking was awarded the Eddington and Albert Einstein medals for his work. So, yeah, I thought that was kind of fun. The fact that, Eddington came around in the very early 20th century in the 1920s, and his name is being used to commemorate future astronomers, astrophysicists, cosmologists, theoretical physicists. And yeah, the same goes with Albert Einstein. So in 1981, Stephen Hawking proposed that information in a black hole is irretrievably lost when a black hole evaporates. Now, this is a very contentious topic because this idea goes against quantum mechanics. And so there will be a couple of quantum physicists that will come out and fully refute this idea because, it pretty much goes completely against the field of science that they're researching. So, yeah, that's one thing that Hawking stated. So, another thing that is created by this idea is a paradox in the connection between quantum mechanics and astrophysics, which was established quite well by the previous works of Hawking, or at least worked towards. And so afterwards, after 1981, Hawking focused on inflation theory, the theory that after the Big Bang, the universe gradually decreased in its expansion. And I think he was working on a theory that showed that the universe itself would have the shape of a shuttlecock. Yeah, a shuttlecock. And I think that's probably one of the first images that will pop up when you look up, Big Bang. So, then Hawking began to work on the Hartle-Hawking state, which essentially proposes that time didn't exist before the Big Bang and basically devalued the idea of the true beginning of the universe. Like, you can get as close as you want to it, but you'll never actually, get to the beginning because that's when time starts. That's like that's the ultimate t equals to 0, A huge piece by Hawking in his career was A Brief History of Time, which is basically the physics of the universe for dummies. That's really all that needs to be said in terms of summarizing the book. This blew him up in the public sphere, which is where Stephen Hawking will be present for a lot of his life beyond the 1990s. Some people would complain about the fact that his disability gave him a lot of popularity, and so other people's theories would be a little bit, shunned. Uh, or I don't even know if that's the correct word. A little bit, put out of the spotlight is what I mean. So also during or late in Hawking's life, he made a lot of predictions which he later conceded on. One of the most hot takes Hawking had was the Higgs boson particle. Um, the fact that it would never be found. And he engaged in a lot of debate with Peter Higgs himself about it, but he was ultimately wrong. He conceded, and he said that Higgs should win the Nobel Peace Prize in 2013, which he did. So, yeah, there were a ton more claims that Hawking made that he was wrong on. He made a lot of wagers with other astrophysicists, which he was wrong on. But yeah, that's just, I guess, one aspect of Stephen Hawking himself. And I mean, that's really all I gotta say about Stephen Hawking himself. If you all enjoyed listening to the last episode of 2023 on astrophysics and cosmology, please make sure to subscribe on YouTube and follow on Spotify if you have not yet. Because I know for a very, very long time that most of my viewers are not subscribed to my channel, and my previous viewer retention rate is not quite high. So I would very, very much appreciate it if you all subscribed. So yeah, that's a wrap on 2023, wrap on season 2. Once again, thank you so much for supporting this endeavor of mine as I investigate all these cool things about astronomy, learn a little bit more about the field of science itself, and build a community. And yeah, I will see you all in 2024. Peace.